Alright, the next thing that we need to talk about before we get into fractions is factors and factoring. This comes from section 2.3 of the textbook. So factor, this is something we've seen before. We talked about it briefly when we talked about multiplying, and so we're just going to review it. So a factor, when we talk about it in terms of fractions and in general, this is a number that divides a given number. For instance, 2 is a factor of 6 because 6 is divisible by 2. We can also talk about factor as a verb. And as a verb, it means that we want to write as a product or as a multiplication. So if I said I wanted to factor 6, we set 6 equal to 2 times 3. Now, one of the things that we're going to get into is common factors and factoring in general. So when we talk about factoring, we do want to know some divisibility rules. So some easy ones to remember. A number is divisible by 2 if it is even, meaning it ends in a 0, 2, 4, 6, or 8. You're probably familiar with that one. One that you might not know, this is a cute little trick to know when a number is divisible by 3. A number is divisible by 3 if the sum of its digits is divisible by 3. To give you a quick example, if we look at the number 18, if I add the digits, I get 9. 9 is divisible by 3, and you should know that 18 is divisible by 3. We can use this rule on more complex examples. Now, another divisibility rule that you might know is divisible by 5. A number is divisible by 5 if it ends in 0 or 5. Just like with 3, we have a similar rule for by 9. A number is divisible by 9 if the sum of the digits is divisible by 9. And the last one that we have is by 10. A number is divisible by 10 if it ends in 0. Okay, so when we talk about factoring, there's two different ways to approach this. The first one is to find all the factors of a number. So what we're going to do is we're going to start with the number 1, and we want to divide the given number by 1, 2, 3, and we're going to keep going. If it divides evenly, we keep the number and the result. If it does not divide evenly, then we're going to move on to the next number. We want to continue until we reach a number that is already on the list. So for instance, let's look at some examples. If we look at 18, I'm going to start with 1. 18 divided by 1 is 18. You will always have this pair. You will always have 1 and the number. From there, we're going to go ahead and go up to 2. Is 18 divisible by 2? Yes, it is. It ends in an 8. It is an even number. 18 divided by 2 is 9. Next number, 3. Is 18 divisible by 3? It is. It's equal to 6. Is 18 divisible by 4? The answer is no. 4 will get you to 16 or 20, but it will not get you to 18. Is it divisible by 5? The answer is no. It does not end in a 5 or 0. Is it divisible by 6? Yes, it is. And note that 6 is already on our list, so we have all of the factors. So our factors for 18 are 1, 2, 3, 6, 9, and 18. All right, let's try another one. Let's look at example B. We're going to start with 1 and 60. 60 is divisible by 2. And if we divide 60 by 2, we get 30. 60 is divisible by 3. If we divide by 3, we get 20. 60 is divisible by 4. How many times does 4 go into 60? Well, 4 goes into 6 one time. 1 times 4 is 4. Subtract, we get 2. Bring down our 0, and 4 goes into 20 5 times. So we get 15. 60 is divisible by 5. It does end in a 0. And 60 divided by 5. 5 goes into 6 one time. 1 times 5 is 5. We subtract, we get 1. Bring down the 0. And 5 goes into 10 2 times. So 5 goes into 60 12 times. 60 is divisible by 6. And 60 divided by 6 is 10. 60 is not divisible by 7. 7 will get you to 56 or 63, but not 60. It is not divisible by 8. 8 will get you to 56 or 64. It is not divisible by 9. 6 plus 0 is 6, and that's not divisible by 9, so the number is not divisible by 9. And it is divisible by 10, which is already on our list. So our factors for 60 is 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. Let's try a couple more. Let's look at 16. We start with 1. We get 1 and 16. It is divisible by 2. We get 2 times 8. It is not divisible by 3. 3 will get you to 15, but not 16. And it is divisible by 4. We get 16 is equal to 4 times 4. We do not need to keep going because notice here we've already kind of rounded the curve. And so my factors for 16 are 1, 2. I only need to list 1 4. You do not need to list it twice. 8 and 16. All right, one more. Let's look at 80. We start with 1 and 80. 80 is divisible by 2. 80 divided by 2 is 40. It is not divisible by 3. 8 plus 0 is 8, and that is not divisible by 3. So 80 is not divisible by 3. We're going to skip it. We go to the next one. It is divisible by 4. We get 4 and 20. It is divisible by 5. 5 goes into 8 one time. 1 times 5 is 5. We get 3. Bring down our 0. And 5 goes into 30 6 times. So we get 5 and 16. Is 80 divisible by 7? Well, just to show you why not, if we divide by 7, we get 7 goes into 8 one time. 7 goes into 10 one time. And we have a remainder, so 7 does not go into 80 evenly. Does 8 go into 80 evenly? Yes, it does. This is 8 times 10. And does 9 go into 80? The answer is no for that one as well. 8 plus 0 is 8. Is 8 divisible by 9? The answer is no, so it does not go into 80. The next number on our list would be 10, but 10 is already on my list. So these are all my factors. We have 1, 2, 4, 5, 8, 10, 16, 20, 40, and 80. Now we will play around with this more in the next section, but when we talk about factors, just note that this is one way to find factors. Now before we get into the next one, we want to talk about prime and composite numbers. A prime number is a number that is divisible by only 1 and itself. Key here is only. Every number is divisible by 1 and itself. Prime numbers, these are the only factors that that number has. On the other hand, we have composite numbers. Composite number is a number that is not prime, which means it has at least one other factor. All of the numbers that we saw on the last slide, they were all composite numbers because we did have other factors. Okay, so we want to know if the following numbers are prime or composite. If it is composite, we want to find another factor. So example A, the number 2. 2 is a prime number. It is the only even prime number. Anything else that is even is going to be composite because it will be divisible by 2. 5. 5 is a prime number. It is only divisible by 1 and 5. 10 is composite. It is divisible also by 2 or 5. Now what about the number 0? What do you think? Is it prime or composite? It's a trick question. This is neither prime nor composite. Most of the ancient civilizations that studied prime numbers did not recognize 0 as a number, so to them all of their rules about prime and composite had nothing to do with 0 wasn't even in the cards at the time. So 0 is actually considered neither prime nor composite. All right, what about 11? 11 is considered a prime number. And 77 is a composite number. It is divisible by 7 or 11. All right, what about the number 1? Do you think it's prime or composite? This is also another trick question. This one is considered neither. And I'll explain why briefly in a few minutes. You don't necessarily need to know why, but it is considered neither prime nor composite. 3 is prime. 19 is also prime. 25 is composite. It is also divisible by 5. 29 is prime. And now for the last one, what about 57? What do you think? The answer is, for this one, this is composite. If you add the digits, we get 12. 12 is divisible by 3, and so 57 is also divisible by 3. So real fast, just to let you know, what are the prime numbers? I'll just list out some of them for you. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. Now this list does keep going on. There's actually an infinite number of prime numbers, which means the list goes on forever and ever. It never ends. But this is a good start for you. So these are numbers that I recommend you memorize so that you recognize them when they come up in problems. Okay, so let's talk about prime factorization. That's why we talked about prime numbers. Prime factorization, this is the result of writing a number as a product or multiplication of prime factors. Now the book presents this several ways, so if you don't like the way that this is presented in the presentation, I encourage you to read the book and see some other methods that they use. I use factor trees. So in order to do this, what we want to do is we want to find two numbers that multiply to the given number. For each of these numbers, which are called factors, we want to determine if it is prime or composite. If it is prime, circle it. If it is composite, factor it again. And then we want to continue until we cannot factor anymore. We're going to write a product or multiplication problem using all of the numbers that are circled. Now I said 1 was not a prime number, and it comes from something called the fundamental theorem of arithmetic. This is not something you need to know. But just for those of you that are curious, it says every natural number is either prime or can be written as the product of primes in a unique way up to order. And so the reason that 1 is not considered a prime number is because of this word unique. It means that there's only one way to do it, disregarding the way that you put the numbers in there. For instance, 2 times 3 is the same thing as 3 times 2. So for instance, this is the only way to write 6 as a product of primes. It's equal to 2 times 3. Disregarding order, you can do it 3 times 2. That is considered the same thing. If we let 1 be a prime number, that takes away this unique quality. I can multiply 1 times 2 times 3. Or 1 times 1 times 2 times 3. Or however many ones you want. And now we no longer have a unique way to write it as the product of primes. That's why 1 is not considered a prime number. Okay, so I digress. Let's go ahead and continue with our discussion. The last thing we want to do is some prime factorizations. So, there's lots of different ways to do this. Okay, as long as you got it, I'm not really going to care how you get it, as long as you show your work. So let's start with 28. Give me 2 numbers that multiply to 28. And keep in mind, it doesn't matter what 2 numbers you pick. For instance, you can go 2 and 14. Me personally, I always like picking the smallest number that divides into the number to begin with. 2 is the smallest number, so I go with 2, and 28 divided by 2 is 14. The reason that I do this is because it's nice and organized. I know 2 is prime, 14 is not. 14 is equal to 2 times 7. 2 and 7 are both prime numbers. Now that I cannot factor any further, I can go ahead and write this out as a multiplication problem. I am only going to keep the numbers that I circled. So we get 2 times 2 times 7. Now one thing that is allowed is you can write this with exponents. So for instance, I can write this as 2 squared times 7. Now just to show you it doesn't matter how you started off, 28. What's another set of numbers that multiplies to 28? If you want, you can go 4 and 7. Is 4 prime? The answer is no. This is equal to 2 times 2. Is 7 prime? The answer is yes. And so notice that we still get the same thing no matter what. We still get 2 2s and a 7. So as you're working through these, I encourage you to go with the numbers that you think work, and then just make sure that our answers check at the end. We should get the same thing. All right, example B. I want 2 numbers that multiply to 40. And there's lots of examples out there. There's lots of pairs that multiply to 40. One that I'm thinking off the top of my head is 4 times 10. 4 is not prime, it is composite, so I can factor it again. This is 2 times 2. 10 is not prime. This is 2 times 5. And now all of these numbers are prime. So we get 40 is equal to 2 times 2 times 2 times 5, or 2 cubed times 5. All right, let's try another one. Let's try 56. 56, what multiplies to 56? I'm thinking 8 times 7. 8 is a composite number. This is equal to 2 times 4. 2 is prime. Oh, I forgot, 7 is prime. 4 is composite. This is 2 times 2. So we get, I'm just going to write in exponential notation, it's a little bit easier. This is 2 cubed times 7. Now if you notice on this one, we have our factors kind of going all over the place. And so that's one of the reasons that I always like starting with the smallest number that goes into 56. For this one, it's going to be 2. 2 goes into 56 28 times. 28, this is 2 times 14. 14 is 2 times 7. And so one of the nice things about starting with the smallest number and going that way is you kind of get this nice picture. I like to call it math topiary, where you can just go in a line starting on the top and going around, and you don't have to worry about hunting for your factors inside your tree. All right, a couple more. Let's look at 60. 60 we saw had lots of factors when we went ahead and listed out all the factors. So now let's look at what it does when we talk about it in terms of prime factorization. So I'm going to go ahead and divide by the smallest number, which is 2. We get 2 and 30. 2 is prime. 30 is divisible by 2. We get 2 and 15. Again, 2 is prime. And 15 is equal to 3 times 5. Both of these numbers are prime. So 60, if I write this in as a multiplication problem, we get 2 squared. There are 2 2's being multiplied. Times 3 times 5. So prime factorization for 60 wasn't nearly as bad as it was when we talked about listing all of the factors. All right, let's try a couple more. Let's look at some that are just a little bit more challenging. Let's look at 120. So again, I'm going to show you that it doesn't matter how we do this. Let's go ahead and go with 12 times 10. All right, 12. What multiplies to 12? I get 2 and 6. 10 is 2 and 5. Of these numbers, 2, 2, and 5 are prime. 6 factors further. This is 2 and 3. So now if we take all of our circled numbers and write it as a product, I have 2 times 2 times 3 times 2 times 5. Remember that it doesn't matter what order you write this in. If I wrote this with exponents, I have 3 2's, so this is 2 cubed times 3 times 5. All right, last one. Let's look at 180. So again, I want to know 2 numbers that multiply to 180. I'm going to go 18 and 10. 18 is equal to 3 times 6. 10 is equal to 2 times 3. I'm sorry, 2 times 5. I got 3 on the brain. And 6 is equal to 2 times 3. So we have our prime factorization now. All of the numbers at the end of my branches are prime. So we can write this now as a multiplication problem. We get 3 times 2 times 3 times 2 times 5. Or we can write it with exponents. I have 2 2's, so that's 2 squared. I have 2 3's, that's 3 squared times 5. Okay, so that's using prime factorization. The main thing is, in order to succeed in this section, you need to know your multiplication tables. Just like when we talked about that multiplication section in the beginning, I'm going to emphasize it again. To be good at fractions, you need to know your times tables, both backwards, forwards, and backwards. You need to know how to multiply numbers. You also need to know what numbers multiply to. Okay, so make sure that if you are still struggling with that, now is some more time to get some practice on it. All right, in the next section, we're going to start getting into our actual fractions. We're going to start with simplifying fractions. So go ahead, take a quick break, and I will see you again shortly.